The paper we're unpacking today is Inverse Knowledge Search over Verifiable Reasoning, synthesizing a scientific encyclopedia from a long chains of thought knowledge base.
Right. And it tackles what the authors call the dark matter of knowledge.
The dark matter, what do they mean by that?
Well, think about any textbook or scientific paper. For cost, for effort, you have to compress the reasoning. You leave out the essential step-by-step logic. You get the conclusion, but the journey, what they call the long chains of thought or LCoTs, it's just missing.
And that makes real verification almost impossible, not to mention finding connections between different fields.
Exactly. So the solution they propose is this massive scalable LLM framework. And it's designed to do one thing: decompress all of that reasoning. It systematically generates and validates these LCoTs from first principles.
So it's building a knowledge base that's just fundamentally different from, the internet that most models train on.
Precisely. The pipeline is built around a Socrates agent. It generates something like 3 million first principles questions.
3 million.
And multiple models have to solve them. Verification is guaranteed because you need consensus. You need the models to agree on the answer. And the answers themselves, they have to be verifiable endpoints, like a number or a formula.
Okay, and with that foundation, they introduced this paradigm shift, a new kind of search they call inverse knowledge search.
Yeah, the Brainstorm Search Engine. So instead of searching for a concept's definition, you search for the full derivations that lead to that concept. It's a total flip.
Which then powers what they call the Plato synthesizer.
Which creates SciencePedia. And they've shown it has a much higher density of actual knowledge points and, this is the kicker, a significantly lower factual error rate. It basically cuts hallucinations way down.
So let's really dig into the problem first. This idea of radical compression of reasoning. We all just sort of assume a textbook is reliable, but the authors are saying this compression leads to two huge failures.
It does. The first one is all about verification. You're essentially forced to trust the authority of the source.
Because the steps aren't there.
The steps aren't there. The scaffolding that connects the axiom to the final theorem, it's gone. You can't mechanically check the logic.
And the second failure.
The second one is arguably more insidious. It's that you sever all these cross-disciplinary links. The path that connects, say, a physical constant to a concept in pure mathematics might just vanish because only the final siloed results get published.
So if you just ask a standard LLM, one that's trained on the internet as it exists today, to write a scientific encyclopedia, it's just going to fail.
It has to. It suffers from this dark matter blindness. I mean, an LLM is a statistical machine. It's built to reproduce the patterns in its training data.
And if the data is compressed, the model spits out compressed knowledge.
And it hallucinates. We all know that.
Yeah.
So trying to build a trustworthy, verified resource on top of that is, well, that's a huge challenge.
So the real technical leap here is what they call statistical novelty. They're basically arguing that a standard pre-trained model has almost zero chance of generating one of these LCoTs. So how did they go from impossible to possible?
Well, they actually proved it mathematically. The probability, they call it t-base-day, of a base model producing a correct, long, multi-step derivation, an LCoT, for any complex question. It's negligible. The data just isn't in the human internet.
So they had to create that capability.
Exactly. They used a technique called reinforcement learning from verifiable rewards, or RLVR.
Okay, RLVR. What does that actually mean in practice for this system?
It means they're not relying on human feedback like, does this sound good? The model is optimized to produce reasoning that ends at a mechanically checkable point. The reward signal is objective. Did you get the right number? Did you derive the correct formula?
I see. So it's not about sounding plausible, it's about being provably correct.
Yes. And this post-training unlocks a totally new emergent capability. Suddenly, their model's probability of success is just vastly greater than the base model.
The reliability comes from the fact that it has to terminate at that verifiable endpoint.
Exactly. And the cross-validation between models just solidifies it. I mean, think about it. The chance that two different models making independent errors in their reasoning would somehow stumble upon the same correct final answer is just astronomically small.
It forces logical consistency.
It really does.
Okay, let's talk about the engine that built all this, the Socrates agent. The fundamental building block here is what they call the LCoT question-answer pair.
Right, the LCoT-QA, it's like the atomic unit of their whole system. It mimics scientific inquiry. You have a well-posed question that demands a deep exploration and that inherently provides a concrete conclusion you can verify.
It makes the whole thing verifiable and navigable. But what I found really clever was their strategy. This endpoint-driven reductionist strategy. They work backward from the conclusions, not forward from axioms. Why do that?
It's all about ensuring comprehensive coverage. They defined around 200 high-level endpoints from a huge curriculum of college and grad courses. By starting there, with the conclusions, they can systematically ask, okay, what derivations lead to this point?
And that generates the prompts.
It generates about 100 prompts per topic, and they fall into two really critical categories.
The first being these reductionist prompts, the what and why.
Yeah, these demand reasoning from first principles. Things like derive the semi-classical equations of motion for a block wave packet, or explain the physical significance of constants of motion. They reconstruct the whole logical structure from the ground up.
And then you have the application prompts, the how.
Which grounds all that theory in the real world. Use a simple pendulum to calculate gravity on an unknown planet, or detail how this specific mass spectrometer works. It connects theory to measurement.
But generating 3 million prompts and answers at this technical level, that just seems incredibly vulnerable to LLM errors. How do they manage the verification at that scale?
With a really, really rigorous multi-stage protocol. It starts with something they call prompt sanitization. A totally separate LLM screens the initial questions for any flaws or bad assumptions.
So it filters out bad questions before they're even attempted.
Right. It catches about 5% of problems right there. Then you have the verifiable endpoint design we talked about, biasing towards solvable problems, and then the most important part, cross-model answer validation.
Where every single prompt is solved by at least 2 different LLMs.
At least 2. And if their answers diverge, even slightly, the whole question-answer pair is just thrown out, discarded.
That sounds expensive, but I guess necessary. Did they quantify how necessary it was?
Oh, yeah. They found that as the problems got harder, the models failed more often. The success rate for a single LLM dropped from around 70% for undergraduate problems.
Down to what?
Down to just 50% for graduate-level topics.
Wow.
So that data just proves it. Relying on a single model, especially for advanced science, would bake in an unacceptable level of error. That cross-validation isn't a nice-to-have, it's a non-negotiable requirement.
So once you have this massive verified foundation, you get to what feels like the main innovation here. The Brainstorm Search Engine and this idea of inverse knowledge search. Why doesn't regular search cut it?
Well, traditional search is basically a dictionary lookup. You type in a compressed term, you get a compressed definition back. It indexes the conclusions.
But we need something that indexes the process, the provenance.
Exactly. With inverse knowledge search, you give it a concept, and it retrieves all the different first principles LCoT chains that end at that concept.
The paper uses the instanton example, which I thought was perfect.
It's a great example. A normal search for instanton gives you the technical definition from quantum field theory. A brainstorm search, though, it gives you this rich tapestry.
What did that look like?
You discover its fundamental role in describing quantum tunneling. You uncover its deep implications in the standard model, how it explains QCD vacuum structure and, baryon number violation, and then you find its surprising use in pure math for understanding 4-dimensional manifolds.
It's not a lookup anymore. It's revealing these non-trivial connections between fields that were severed by the old compressed way of doing things.
It turns search into genuine exploration. And all of that validated, interconnected knowledge is what feeds the Plato agent.
Right, the synthesizer. And it's doing structured synthesis, not just, riffing. The LCoTs are its reasoning scaffolds. But how do we know it's not just generating plausible-sounding nonsense?
Well, you look at the metrics. And the metrics are really compelling. They ran quantitative tests across 6 big disciplines: math, physics, chemistry, biology, engineering, and computation.
What did they find?
The articles synthesized by Plato consistently showed a substantially higher knowledge point density than a baseline LLM.
So more verifiable facts per paragraph, essentially.
Exactly. And on the reliability front, grounding it all in those pre-verified LCoTs led to a significantly lower factual error rate. They cut hallucinations by about 50% compared to the baseline.
And the final encyclopedia, SciencePedia, has a deliberate structure to it.
Very deliberate. It has about 200,000 entries, and Plato organizes the LCoT data into 2 core sections: Principles and mechanisms, your what and why and cross-domain applications. That structure forces it to include those emergent connections.
They even say the writing style is inspired by Feynman's lectures.
Right, aiming for that intuitive, insightful, advanced popular science feel.
The Transmon Qubit case study they included really drives this home. What does the SciencePedia entry give you that a standard LLM description misses?
Okay, so the baseline LLM gives you the generic stuff. It's a building block for quantum computers. It simulates nature. Plausible but shallow.
Right.
The SciencePedia result, built from the LCoTs, gives you verifiable depth. For instance, it shows you the exact derivational path connecting the Transmon's specific design ratio, e large and much greater than EC/ET, directly to why that mitigates charge noise. It even brings in the charge reservoir analogy.
And it connects it across fields in ways you'd never find in one place.
Systematically. It details its use as a quantum microscope for probing Majorana's zero modes, its role in cooling macroscopic mechanical resonators, even its application as a tiny lab to test the Leggett-Garg inequality, which is a concept from non-equilibrium quantum thermodynamics.
These non-obvious connections are the whole reward for building that foundation in the first place.
That's it.
And they actually went and empirically confirmed this interconnectivity with a huge network analysis. What did that show?
They built this massive graph with over 120,000 keyword nodes. And using some network science, modularity belief propagation, they found this clear hierarchical structure. But crucially, they measured a high density of non-trivial connections between the different scientific communities.
So it's empirical proof.
It's empirical proof that the process worked. It successfully captured and mapped that hidden cross-disciplinary dark matter.
Now, the authors framed this whole automated framework as a solution to the cold start problem.
Yeah, that's their ultimate position. This is an automated, scalable way to build a massive, verifiable foundation of knowledge from scratch. Something that, volunteer efforts like Wikipedia would really struggle with, especially at this technical level.
Looking forward, though, the vision isn't just a purely AI-driven encyclopedia. They see it becoming a hybrid model.
Yes, absolutely. The goal is to combine this AI-driven scale with critical human expert refinement. They talk about creating interfaces that let the scientific community contribute, validate derivations, suggest corrections to keep it alive and accurate.
That integration feels key. But what's the ultimate, most ambitious long-term goal here, beyond just the encyclopedia?
It's the full formalization of the knowledge network.
Meaning
Moving beyond just natural language. They want to apply mathematical logic and automated reasoning to parse all these LCoT chains into a formal, machine-readable graph. Imagine what you could do with that.
it's not just an encyclopedia anymore.
It's a fully automated discovery system, one that could formally check the consistency of new scientific theorems against the entirety of known, verified science. That's the endgame.